Yes. Alternating current. Okay.
Rectification is the process of converting alternating current to what? Direct current.
Direct current.
AC to DC. So most of the times, our circuit runs on DC, all right?
Yes.
Yeah, but sometimes we want to be able to use alternating current to power the circuit. In that case, the first step is actually to convert the alternating current to direct current, all right?
Okay.
If you look at the graph of AC, it is sinusoidal in nature, right? That wavy kind of graph. I don't know if you've
Yes.
seen it before.
Mm,
Okay, let me show you.
something. I've seen something.
Let me show you.
Okay.
Yeah. So this is the graph for an alternating current and the graph for a direct current. For an alternating current, it starts from zero. That is, there was no current at all. So by the time the power supply is turned on, it starts shooting up until it gets to the desired or the desired voltage, maybe 220, 120, or 240, or whatever. So it gets there, then it starts climbing down. It crosses line 0, then goes down to negative. And when it gets to minus of the amplitude, the negative of the amplitude, it stops and go back up again. So it continues that cycle like that. This is what we call it alternating. The current is alternating between the positive side of the graph and the negative side of the graph, passing through line 0. Do you understand? So
Yes.
this is the kind of current that powers our appliances, our light bulb, our computer, our microwave, our fridge. But the point is that this thing happens so fast that you don't see your fridge turning off and coming back on. The time it takes to switch between one um, the one side of the graph and the other side, that is between positive and negative, is so fast. It's about 50 times in 1 second. So in 1 second, we have 50 of this cycle in a single second. So it takes 1/50 seconds for the wave to complete one cycle. So between this point 0 here and this other one at this end is one cycle. One cycle is a combination of one up and down movement of the current within this graph. So this is a cycle here. So what we have in the screen here is 1.5 cycle. Do you understand?
Yes.
So half of the cycle is up and the other half is what? Is down.
Now.
So this is what happens in your cable that takes electricity to everything you have in your house. As for the other one here, this is direct current, right? So
Yes.
this direct current, the graph, you can see it is a straight line. This is the graph
Yes.
actually. This is the 0 line. At point 0, it begins from the exact point. This is the kind of voltage you have in your battery. If your battery is 1.5 volts, you get 1.5 volts, like continuously, smooth.
Yes.
So the only thing that will make this thing change is when your battery starts becoming low. So maybe it was initially 4 volts or 3.7 volts, and it drops to 3.6. Then this graph will come down a little bit by 1 volt, but yet it is still continuing on a straight line. Do you understand?
Yes, I understand.
So this is the difference between AC and DC. As for AC, it is turning on and turning off at a speed of 50 times in 1 second. As for DC, it is not turning off at all, it's just on. If you measure the voltage in your battery right now, it is still there. If you measure the same voltage tomorrow, it is still there. Do you get it? But for this one,
Yes.
at every point in time, it is turning off and turning on. That is the nature of this. So they have advantages, the two of them, they have disadvantages. There's a whole lot of usability around both AC and DC. One of them, let me quickly mention, is that as for AC, AC can travel long distance.
Long distance.
It can travel long distance without weakening. If you send AC signal from the north to the south, right, the
Yes.
voltage reduction will be very, very minimal. But within your room, the room where you are right now, if you send DC
Yes.
from your window to your door, it will have reduced drastically.
Hmm.
Do you understand? So in order to transport
Yes.
electricity from one end of a community or a country or place to the other end, we are going to use AC. Then whenever it gets to its destination, you cannot convert it to DC for usage within a small geographic environment, such as maybe your table, between your socket and your laptop, within a very small environment, a very small distance. Do you understand? So
Yes.
they both have their pros and cons. You get it? Now,
Yes.
the point here is when we talk about rectification is trying to convert this symbol, this wave here to this wave, because that is what makes them different. What makes DC DC is because the waveform is straight. Are you there? So from what's on the screen now, the first graph here shows what an AC current looks like. Here's how it works. It increases until it gets to the maximum
The
desired voltage,
maximum.
then it continues to come down. All this happens immediately. It happens within a short span that is equivalent to dividing 1 second by 50. So that time is very, very tiny. So all this happens. It takes one of that time to complete one cycle. Okay? So now
Yes.
what we have here next, half wave rectifier. Now, rectified. Now, do you see this graph here? This is what you
Yes.
get when you use a single diode. What does that even mean? It means that the wires transporting AC current, in that wire, the current is going up and coming down. That's the meaning of this first graph. Do you get it?
Yes.
But when you use a single diode, remember we said that a diode can allow positive voltage to travel from anode to cathode, right?
Yes.
And this top side is the positive, right? And this is line here is 0. The bottom side is the negative. Is that correct?
Yes.
Now,
Yes.
because a diode will only allow positive to pass through it, only the positive part of the wave is what will pass through the diode. You know, negative cannot pass through
Okay.
diode, all right?
Yes.
And that's why this is what you get when you use a single diode between
Yes.
AC and the load. So this is the kind of waveform you get. So eventually you notice a kind of on and off, because this gap here, although it is very, very small, all right, but
Yes.
within that line, what you have is 0.0 volts, all right?
Yes.
So as the voltage is trying to travel up until it gets to the desired voltage rating,
Voltage.
the diode will work. It's going to allow the flow. Then once it gets to the negative side, the diode will stop working, which means the current will no more flow, right?
Hmm. Yes.
Now, what's the essence of full wave now? This next, the next graph here shows the result of a full wave. For a full wave, there is not going to be a blind spot because the diode set up in the case of a full wave. We
Yes.
have not done full wave in the class. We are going to show you next now after these images. Right? So for a
Okay.
full wave, it allows two diodes to work at a single time instead of one diode. The graph you have here is the result of one diode. What we have here is the result of what? Two diodes working.
Two diodes.
So when diode 1 is off, then diode 2 will pick up immediately. Do you understand?
Hmm.
So that
Yes.
we are going to have consistent flow of current. And gradually we are approaching DC. Is that not correct?
Yes.
We are gradually approaching DC with this. So the essence of rectification is to convert AC to DC. The primary difference is that for an AC, there is wave on the negative side, while for a DC, there's no wave on the negative side. It's only on the positive side, right? For an
Yes.
AC,
Yes.
the signal is sinusoidal. This shape here is called sinusoidal, all right? It's a sine wave, all right? For a
Okay.
DC, it's a straight line. It's a straight line, all right?
Yes.
Okay, so how can we now implement a full wave? We have done half wave, all right? We have done half wave. How can we now
Yes.
implement a full wave? A full wave is implemented using four diode network. So four diodes are going to be connected in a particular network of circuit that will allow them to interchange functionalities when the signal is supposed to blank out. When the power supply is supposed to be zero, another diode will take over and supply power at that point in time. So when another half of the sinusoidal wave is supposed to blank out, another diode will take over. So we are going to look at that in the class now. When dealing with diode, there is a concept called voltage drop. Voltage drop is actually the amount of voltage that is reduced by that element or component. So
Okay.
if you transfer a voltage to a diode, by the time it comes out on the other end, there is a small amount of voltage that has been utilized by the diode, and as a result, it doesn't come out completely. Do you understand? It's like passing a
Yes.
hose. It's like passing a hose through a machine and the hose supplies maybe oil. Maybe the machine itself is going to take a small portion of that oil to lubricate itself. So which means that the final amount of oil, the volume amount of oil that will be coming out will have been reduced by a small amount. Is that correct?
Yes.
That's exactly what happens in a diode. So when you connect a voltage to the anode, right? The voltage at the cathode is equal to the anode voltage. Let me say V out is equal to V in minus approximately 0.7.
Okay.
Do you understand?
Yes.
So it's usually not up to that. It depends on the kind of material that was used in making the diode. Sometimes it can be germanium and it can be uh, germanium diode. If it's germanium, it has a certain amount of voltage that goes away. Then other components have their own, but generally we take 0.7 just for theoretical understanding. Okay, so and since your circuit is not critical to the needed voltage, so a difference of 0.1, 0.2 will not really make any difference. Is that correct?
Yes. Yes.
So, so we take 0.7. So if you supply 9 volts in this case, by the time you read the voltage coming out, you'll be
Maybe
getting
8.3.
around 8.3, not 8.3, around 8.3. So I'm
Okay.
going to use a multimeter. I'm going to use a multimeter to test the output voltage. Okay,
Yeah.
so we have a multimeter here and it's already set to voltage. Then we connect positive to the cathode or the diode. Likewise, we connect negative to negative.
The negative point on the battery.
Yeah, negative going to the battery. Why? Because we don't want to influence the negative by the diode here.
Okay.
Okay, so we want to see what's coming out from there, and let's simulate and see. So here you can see 8.41, that's about 0.59,
Yeah.
right?
Yes.
Yeah, 0.59. So what you get from that point is different from, if you check using another meter, you will realize that the input is more than that. So the input go straight to the battery. Then also want to go straight to the battery. Okay, so let's see. So you can see the input is 8.99, almost 9 volts. Then the output is 8.41. Do you get it?
Yes.
So in reality, it's this 8.4 will be something around 8.4, 8.3 or so. Okay? So
Yes.
now, as I said, a difference of 0.1 or 0.2 will not be significant enough to affect. But right now, we know that, okay, something is missing from the voltage, a very small amount of voltage. Now, let's say the load is not there. You are not going to get to know what's going on, because if there is no current from the load, if the load is not taking any current, you will not be able to measure the voltage difference. Okay, so with this now, you have seen, okay, let's also try the cathode end, and you realize we don't really have much for the negative. So we had 8.4, and the difference, look at it now. We had 8.4, and we also have 8.4. You can see the reason why I have to choose from the battery directly.
Yes.
What do you think is going on here? Between here we choose between the battery, which is almost 9 volts, and we chose the end of the battery too. So we are getting what was coming out of the battery, right? Before. But now we are not
Yes.
testing the voltage before the diode, sorry.
But
So we're testing the voltage before the diode, So here we're not testing directly from the source. So the 8.4 we have here, now there's a test for you. There's a test for you. The 8.4 we have here, what is influencing the voltage? What is reducing the voltage? Is it this diode or this LED?
is it for the second
This one.
multimeter?
Yes.
Okay.
The answer is it is this diode. Why? Because the negative have not even gotten to the source. At this point, the voltage here at this point is 0, right?
Yes.
So what we are still having here before this point is tending towards positive. It has not gotten here. So by the time it travels between the bridge here, between the anode and the cathode, this anode will take its own voltage.
Okay.
So what we are going to get at the point of the day will not be compared with 0. It will be compared with something minus 0.5, 0.6, 0.7. So
Okay.
that difference is what we are getting on the meter here. That's why if I put this wire at the other end here, the cathode end, I wouldn't see any difference. It's more or less like placing the wire on the battery terminal. Do you understand?
Yes.
There is a kind of, it looks kind of tricky because we are dealing with the negative side now. Okay, so if you want to get how much voltage is the lead, how much voltage is the lead taking, how can we measure that? How do you think we should be able to measure that? We should be able to measure that, but how?
By connecting
By connecting what?
the positive of the multimeter to the anode of the LED, then the negative of the multimeter to the um, anode, sorry, to the cathode of the diode.
That is the terminal of the battery. The cathode of this diode is the terminal of the battery. The cathode of diode 2 is a terminal of the battery. This is the cathode here. Is that not?
Yes.
Okay, let's see what you have. You know what you have?
2.5.
You have the voltage of the lead plus the voltage of the diode.
Mm.
Hmm? Hello?
That part is I don't understand.
Yeah, it's very clear. It's very clear. What you have between the red wire here and this black wire here for the meter,
Yes.
you
Yes.
have two components. One diode, which is the lead, and another diode, which is the power diode here.
That yeah.
So the lead is taking about 1.8, 1.9 volts, while this guy is taking about 0.6, 0.7 volts. If you want to see the actual voltage being taken by the lead, you have to connect to the negative of the lead, like this, which is the cathode.
Okay.
So once you run it, you will see it. You can see that 1.94.
Yes.
So if you subtract 2.5 something from 1.94, you'll be getting around 0.6,
Yes.
which shows that that voltage is for the lead. Do you understand?
Yes. 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 Yes.
So, so this is just meant for you to understand. Now you have been able to touch, okay, how to do test points. Testing each point in your circuit. Okay, I want to test. Now let's also check how much voltage is passing through the resistor, right?
Yes.
The resistor's responsibility is to reduce voltage.
The voltage here.
Let's see how much voltage is passing through that guy. It's usually called current limiting resistor. Now 5.89, right?
Yes.
5.89. So which means if you take 5.89 is what this guy is responsible for. The leftover is being shared by the lead
And
and
the packet.
this diode. And we got, what did you get there the other time? 2 point what? 2.5 something.
2.5 something.
2.54 so, or 2.56. So if you add
2.56.
2.56,
Yes.
if you add that to 5.89, what do you get?
That is 8 point something.
That is about 9 point something.
Hmm?
5.89 point 2.5 something is about 9 point something.
Hmm. Yes. Yes.
Okay, plus 2.5 is about 8. Okay, 2 point is about 8. 8 point something. 8.3. 2.54. 8.34.
Hmm.
The remaining voltage is for this diode to give us 9. Do you
Yeah.
understand? At the end of the
Yes.
day, we are already doing circuit analysis gradually. At the end of the day, the total voltage consumed by each and every component must be equal to the voltage supplied from the source. Do you understand?
Yes.
That is, this component A, component B, component C, and component D.
Okay.
The voltage consumed by each and every one of them, if you sum them up, you are going to get total voltage from your console.
Hmm.
Okay, so let's proceed with rectification. In rectification, we need an AC supply. We need an AC power supply. So, for an AC power supply, we need, let's see if we can get one power supply. Can get power supply. So we have a power supply here, and this power supply will be getting our AC from it. Okay,
Yes.
so we are using a function generator instead of a power supply. Workbench is giving us. DC instead of AC. So we decided to use a function generator that can give us actually sinusoidal wave. All right. So with this, we can now supply this AC to through a diode to a circuit. But I would want to use a meter to confirm the output. Check the output. So we have this. Then we have this. So by the time we run it, we should be getting 30 volt AC. But this guy was designed for DC. So
Okay.
it was designed for DC. So we can't get something.
Is it a function generator?
No, this
Okay.
meter was designed for DC. So we're supposed to get this 30 volts. So let's see what we can do. We are going to supply the voltage here. We're going to supply it through a diode.
Okay.
So by the time it passes through the diode, the output will not be a complete AC, although it will be a complete DC as well. So there's a number of stages that needs to go before final. So let's bring in a diode. Okay. So if you pass this voltage, this is AC voltage, and we measure with this DC meter, then we'll start having some meaningful output. Okay. You will see the difference that the DC voltage is climbing up gradually, right?
Yes.
Compared to before the diode. Now, by the time we rectify the other side, we'll be able to have something more meaningful. Why? Because the diode is taking the voltage, is making the voltage appear more DC than AC. For the first measurement we did, the positive side, we have cut off the negative part of the wave. So, but the negative side is still fully sinusoidal. So let's check now. Oh, it's reducing. However, it's becoming close to this. So I would have loved if you have an AC meter in this application, so that we can also measure what's going on the AC side. So the point here is, by the time we are done with the full wave rectifier, you will not need to be careful of which point is positive or which point is negative in the AC. The rectifier itself will adjust itself. That's one. Number two is that there is a number of stages that comes after the diode rectifier stage that allows the voltage to climb up a little bit again. During the
Okay.
rectification, the voltage drops. One of the reasons is that the diode voltage drop is involved, right? So, in
Yes.
order for us to rectify, what are the different stages that are involved? Is the complete stage, the process it takes in order to fully rectify a circuit. There is a number of different ways it can be done, but this is one of the simple ways. So the first stage is the AC supply. That is the power supply from the grid, PHCN,
Okay.
NEPA, stuff like that. So it's usually kind of high, you know, although it is low voltage anyways, but for our electronics class, it's a high voltage, 240
Okay.
volts, 220 volts. Because that's not what we need. We needed something very small. We needed 5 volts DC. And we have 240 volts, 230, 220 volts. That's kind of high, right? So the first thing we
Yes.
do is to first of all step down that voltage. That voltage is much. So we
Okay.
can step it down from maybe 220 volts, you know, maybe to something around using a step down transformer. So you can step it down to something around 12 volts AC. Can be 12 volts or 15 volts. Yet it is still AC. Alright?
Yes.
So you can step it down to 12 volts or 15 volts. The windings on your transformer will determine how many voltage you get. If you are the one
Okay.
winding your own transformer, you are going to wind specifically for what you need. However, the most important thing is that the voltage from this transformer must be higher than whatever voltage you need. It should be a couple of times higher, maybe 3 times or two
Okay.
times so that you will not have deficit. No. So next stage after this, by the time the voltage has been transformed from high volts to low volts, then the next thing we want to do is to actually do the rectification. This is where our diodes network will be needed. So the rectification we are going to be doing here is full wave, or let me just call it rectification, rectifier. So the rectifier is a stage where the AC is actually converted to DC. I have explained to you using those graphs that what the rectifier does is to cut off the negative side. And if you are using half wave, it's only going to cut off the negative side and we are going to have blanks, blind spot. Did you remember that? But if you are using
Yes.
full wave rectifier, there is not going to be blind spot. Throughout the life cycle of the voltage supply, we are going to have voltage, constant voltage. However, it's going to be, it will be reducing and increasing because of the wave. But the next mission here after rectification stage is to remove that wave.
Okay.
That, remember that wave from that half wave, right?
Yes.
So how do we do that? We are going to use, I told you before that we're going to use 4 diode here. So for those 4 diode, 2 of them are usually active at a time. So if you switch the polarity of the AC power supply, then the other 2 will be the one active. So doing the job of those 2 diodes that we drew in our circuit the other time, you remember that circuit? We have one diode
Yes.
on the positive, one diode on the negative. That is exactly what we want to be achieving every now and then. But the automatic transition between one set of diode and another set is what this rectifier does whenever you switch power supply polarity. Okay?
Yes.
So next we have is after the rectifier, we have a stage where we have to smoothen the voltage. You know, at that point, the waveform is still there, but it is half now. We have half of the wave, even though we have rectified fully. But the half of it is still there, but there is no blind spot. All right?
Yes.
So what we're going to do here in this stage is to add smoothing. Smoothing is a process of making your DC voltage without noise. That thing you have here is going to be causing, yeah, it's going to be detected as DC, but you will not get a full DC. You know why? Because it is still going up and coming down, but it's not passing through zero. So in
Okay.
order to smooth, we use a component. It's usually capacitor. So a capacitor has a special feature, and the feature is that it allows AC to pass through, but it blocks DC. Take it carefully. The capacitor we are going to be using allows AC, but blocks DC.
DC.
So AC will pass through, DC will not pass through. What is AC? AC is that sinusoidal wave traveling from positive end to the negative end, going back to the positive and coming back to the negative. Do you understand? While
Yes.
DC is the one maintaining only one side, which is the positive side. But by the time we achieve rectification, then we will have achieved DC. However, this DC is not smooth. There's still a kind of AC there because it's still traveling, but within the space of positive realm, positive domain, right?
Yes.
So what exactly is the capacitor doing? The capacitor is going to do two things. Number one, in fact, probably it's going to do one thing, smoothing. And how does it do it? It does it in two ways. Number one, by ensuring that anything that looks like AC, it passes through the capacitor and goes to the negative side in order for it to go and recycle at the transformer end. Do you get it?
Mm.
Or
Yes.
at the diode end. At the diode end. So the diode is going to transfer it back to where it's supposed to go. Then secondly, the capacitor is going to store the current. So when the waveform was like, let me show you again. That's okay. So here I said again that if the capacitor is at zero, that is there's no charge. By the time this power is supplied, everything coming in will go into the capacitor as long as it is DC, it is this positive end. But
Okay.
whatever part of the current that appears like alternating current, it will pass through the capacitor. It will not stay, it will not charge it. It will just pass through it, and the capacitor will allow it to flow to the other pin. You know, there are two pins to a capacitor, the positive and the negative, right? So the voltage
Yes.
here, you pass through the positive, and if it is AC, it will only pass through the negative and go. So the capacitor allows AC to flow through it, but it doesn't allow DC. It blocks DC. So since the capacitor itself is empty, it's going to contain this. It's going to get charged with this DC coming in. All these are DC. But the difference is that it is not smooth, right?
Yes.
Now, the capacitor, by the time you start charging, after a while, after a very short while, the capacitor will have charged. Maybe the entire voltage coming in is about, maybe it's about 10 volts. Or let me say 10 volts coming here, right? You know, or let me say it's about 15 volts. Let's say the voltage coming in is about 15 volts, right?
Okay.
And the diode have taken about 1.5. So maybe what we have now is 13. So what is coming maximum here is 13, but it still goes back to zero, then climb up to 13, goes back to zero, climb up to 13, goes back to zero, right? So the capacitor will be
Yes.
getting charged. It will be getting charged. As the capacitor is getting charged, this voltage will not be able to land on zero. The minimum point it will be able to stay is where the capacitor has charged. The capacitor
Okay.
is no more allowing it to get to zero anymore. So gradually we are approaching DC. Is that right?
Yes.
So as the
To
capacitor is
keep going straight.
yes, as the capacitor is increasing, this wave will not be able to go down anymore. It will keep going up. It will keep maintaining up. So by the time it travels up, instead of it will come down, but it will stop maybe somewhere around here because the capacitor has charged
Okay.
to around maybe 7 volts. By the time the
Okay.
capacitor charged to maybe 8 volts, the next wave will stop around here. You can see how we are approaching DC.
Yes.
So the moment capacitor gets fully charged, the line will almost be straight. It will not more be going down and coming up. Can you see how the capacitor
Oh.
helps us in achieving smoothing?
Yes.
I wish to show you what that looks like. We are going to have, after this stage, the next stage after the capacitor is what we call ripple. So it's going to have a kind of ripple, showing that the voltage is still trying to go up and down, but the capacitor is not allowing it. So there's going to be a kind of ripple. You know, ripple is when the water is not fully smooth. There's a kind of noise on the
Mm.
water. You know, that's that thing that wave on a
Yes.
gentle water, but it is still there's a breeze blowing the surface of the water, so it gets a kind of ripple. So that thing is called ripple. So we still get a
Yes.
ripple in the voltage. But from that point, you can supply your circuit directly because it is already DC. Do you understand?
Okay.
So we just need to
Yes.
remove the ripple from the something. So there are a number of ways in which ripples can be removed. So the next stage after smoothing is voltage regulation. So it is in this voltage regulation we are going to now set our desired voltage. You know what we have there was about 13 volts, and right now the capacitor is involved. The capacitor is involved, so we're not going to be having up to 13 volts. So with this voltage regulation stage, we are going to be able to regulate the voltage that is coming to an exact voltage that is needed. So if what we want in our circuit is 5 volts, this is the stage where we are going to set it to 5 volts. So even if the voltage coming in is about 20 volts, cannot get more than 5 volts. Do you get it?
Mm. Yeah.
So we are going to use a voltage regulator for this one. So for this one, this is the power supply from the grid. This here is a transformer, the step-down transformer. Here is a set of 4 diodes connected in a network that gives us the rectification results. Now here, smoothing is simply adding a capacitor to this stage. Then the capacitor is used to do what I've mentioned. Then here we have voltage regulation. So the voltage regulation is including a voltage regulator. A voltage regulator is a device, is a component that allows you to get a stable voltage output. Do you understand?
Yes.
Okay, so for now we are going to stop here. Then next we are going to implement this in the class. Although
Okay.
after this voltage regulation, it is usually recommended to have a last stage, which is another stage of smoothing. But here this time around, we use this one to prevent shutdown. The
Okay.
smoothing here is different from the smoothing, the first one. Here, this one is used to, because after the regulation, sometimes you still have a very small amount of noise. So this one is used to remove the noise and also helps to reduce the um, tendency of shutting down this voltage regulator. So the voltage regulator usually shut down when you try to demand, when your circuit tries to demand more than what it can supply in terms of current. You know? So we are going to discuss that once we have put up our circuit completely. Okay, for now, let's take a break.
Okay.
We'll come back soon.